Hello, Kim students. We're going to study light today. So if you'll turn to your study guides to lesson 4, the wave nature of light, we'll go ahead and get started with that. All right, you should have your study guides open and turn to lesson 4, the wave nature of light. Now, for the past couple of lessons, we have been focusing on the structure of the atom, specifically looking at an historical approach to the structure of the atom, looking at various major players on developing our current model of the atom. We started with the early Greeks, and then we talked about Democritus. We looked at John Dalton, and we looked at J.J. Thomson and Ernest Rutherford, and all of their contributions to developing the structure of the atom, the experiments that they've conducted, and yeah, just some of the things that they've done that's really important. But we're going to have to take a pause for a moment and turn our attention to a new topic, and that is the nature of light and what light is and what its structure. And we have to do that in order to really begin to understand any more about the structure of the atom. And so for the next few lessons, our attention will be focused really on light more than anything else, okay? So let's get started here. So first of all, it has been known for a very long time that light is a wave, or at least it has a wave nature to it. Usually we refer to the waves of light as standing waves. And if you don't know what a standing wave, I'll take a moment and kind of explain what a standing wave looks like, its characteristic properties, and so forth. Things that you need to be aware of for the test. So essentially, let's demonstrate a standing wave by using a rope that you see in this diagram. So let's say you take one end of the rope and you hold it, and the other end of the rope, you're going to tie it to a wall. So it's in a fixed, this end is in a fixed position, okay? So in order to create a standing wave, you must have one side of your rope absolutely tied down or in a fixed position so it doesn't really move. On the other end is going to be some type of device that creates oscillating motion. It could be, in this case, your hand. It could be a particle. It could be something, anything that is basically creating oscillations or vibrations. So our hand here is going to hold this rope, and it's going to start moving up and down in creating oscillations. When that occurs, the rope begins to create waves. In other words, energy is going to propagate out of your hand through the rope in this direction towards the wall. And in doing so, that energy is transferred in the rope, and that transferred energy creates a wave, or in other words, a standing wave, because once it hits the fixed end, that wave is going to more or less go back in the other direction instead of continuing on. And the wave doesn't stop. In other words, it goes to the one end and then comes back out in the other direction, okay? And so as long as your hand is creating those oscillations, the wave is going to be doing this, all right? If you change your oscillations, in other words, you might add more energy to the rope. As you're adding more energy to the rope, you're going to get these high points that you see here, and you're going to get these low points. And I'm just going to kind of mark them here, low and high points. The high points of the wave is known as the crest, and the low points are known as troughs. So you're gonna essentially, again, the hand is generating energy, and that energy is moving through the rope, And as it's doing so, it creates a displacement of the rope, creating a wave. And again, it's moving in this direction. And you create these crests, and then you create these troughs. And then once it hits this wall, it's going to start going backwards in the opposite direction, creating the crests, and coming down, creating the troughs, and then back again. And this continues to go on as long as the oscillations are occurring. Okay. The last one here, we've increased our energy a lot more. And so now we're getting several wave crests and several wave troughs due to the increase of energy of our oscillating hands. Okay. Another great example would be certain musical instruments, especially the ones that have string instruments, like a guitar, for instance. So a guitar, you have several strings, and sorry about that, lights went off. Several strings that are connected to the guitar at both ends. And one end is going to stay fixed, while the other end is going to get some movement, oscillating movement by your hand. As you're plucking the strings, it's going to create vibrations or oscillations. And those oscillations are going to move through the strings, and they're going to create standing waves. As you can kind of see here, the standing wave here is created by the strings. You see the high points and the low points in the string. Now, these oscillations that are creating standing waves will result in essentially helping to create music with the guitar, okay? And all string instruments work in this manner using standing waves. Okay, I'm going to take a moment and show you a simulation. Get to it here. Simulation, hopefully I can find it. Let's see here. There we go. There it is. All right. So I have this simulation of basically on the left-hand side here is some kind of, I don't know, machine, device, whatever, but it's oscillating up and down. And as a result, the energy from this oscillation is creating a wave that's propagating in this direction here, okay? But it's not a standing wave. We do see high points, which are the crests, and the low points are the troughs. But the reason why it's not a standing wave is because over here, we don't have a fixed end. Instead, the wave is continuously going out this window. I guess that's what it is, a window, and keeps on going on. No fixed end. So we don't have a standing wave, so we need to create a standing wave. So I'm going to do that. See, fixed in there. There we go. Now we have a fixed end right here. And so now the wave is still propagating in this direction, but when it hits that fixed end, it's going to actually start going back. And if you look really close, you might actually get a feel of that. And it almost feels like, here's this midline right here with this dotted dash lines. It almost feels like the wave is kind of rotating around this dash line. And that rotational feeling is because the two waves are propagating in opposite directions. And if I slow it down, you might be able to see that a little bit better. Slow this down. Kind of take a look, and you'll kind of see that it feels like you get this sense that the wave is sort of rotating around that fixed line. Okay, and again, it's really not. The wave is propagating in the forward direction away from the oscillations, because the oscillations are creating energy, and therefore that energy is transferred as a wave to the fixed end, and then they create a wave coming back in the direction of the oscillations. Okay, hopefully that makes sense about standing waves. We're actually going to come back in a little bit later and look at this simulation some more. Okay, so let's go back to our notes here. All right, now let's take a look at some specific characteristics of standing waves that I want you to know and understand. So we talked about, again, that the high points on the wave are known as the wave crests, and these low points that we see are known as the wave troughs, okay? The height of the wave is known as the amplitude, okay? And the height of the wave is measured from this midline. That's the line that goes directly in the middle of the wave and represented by this dashed line here. So the midline to the top of the wave crest, that distance is the amplitude. You can also get the amplitude from the midline to the very low point of the trough, okay? And that distance from midline to trough or midline to crest is the same amplitude, same distance. We also have a characteristic known as the wavelength, and the wavelength is determined by the distance between the top peak of one crest to the top peak of another adjacent crest, okay? So the distance from here to here is the wavelength. We can also get the wavelength from going from the low point of one trough to the low point of another adjacent trough. And the wavelength from trough to trough or from crest to crest is the same distance for that wave. So it doesn't matter where you actually determine. In fact, if you could also determine the wavelength, if you take a point here on this wave to the point over here, the same location, the distance from each point here is also the wavelength, which is the same. So basically we can determine the wavelength in a variety of ways. Now, the symbol that I just wrote that looks like kind of an upside down Y is really known as the Greek letter lambda. And for our purpose, it stands for the wavelength. So whenever you see lambda, this upside down fancy Y, we're talking about wavelength here, okay? All right, so here's some definitions of wavelength that you can put into your study guide, your notes there. Again, the wavelength is the distance between two consecutive peaks, and that's crests, right, or troughs in a standing wave. Really, I also think that you should understand the units that we're going to be looking at as far as standing waves is concerned for wavelength, and that's going to be either in meters or in nanometers. Light, since that's what we're really focusing on, the wavelength of light, the units are usually in nanometers, okay? So please write that down and make note of that, okay? Those units. All right, so we talked about the amplitude. Let's come back to the frequency in just a moment. The amplitude we talked about was that vertical distance from the midline of the wave to the peak or trough, okay? Now, the amplitude of the wave, as far as light is concerned, is important for looking at light's intensity as well as the brightness. What you could pretty much say in terms of what you have to know about the amplitude is that the higher the amplitude, the brighter light will appear, or the more intense it is. If you've ever seen a really bright light before, maybe from the headlights of a car and it's shining in your eyes, it's not only really bright, but it's really intense too. And so intensity of the wave and the brightness of the wave are related through the amplitude, the height of the wave. And again, the higher the amplitude, the more intense or brighter it is, okay? So now let's go to our frequency. Now the frequency might be the more challenging term to completely understand when it comes to standing waves or light in general, but absolutely critical in our discussion of light. So by definition, frequency is known as the number of wave cycles per second that pass a given point in space. So maybe you can visualize this. Let's say you have a wave that we're creating here, and you have a crest and another crest, okay? So the distance from one crest to the other crest is the wavelength, okay? That we know, all right? Now, that whole thing from crest to crest is also known as a period, okay? So essentially what we're gonna do is take a point in space, it doesn't matter where that point is, and what we're gonna do is we're gonna count the number of periods or cycles. And okay, so you could say from crest to crest is a cycle, okay? Crest to crest is one cycle, okay? And so what we're gonna do is we're gonna count the number of cycles that pass this point in exactly 1 second, okay? So again, we have this cycle from crest to crest, and we're going to take that unit and see how many of those pass a given point in 1 second. And that will tell us our frequency, okay? So if you think about this, if the cycles get smaller, in other words, if the wavelength goes smaller, then the number of cycles that pass a given second increases, all right? But if the cycle gets larger, or in other words, the wavelength gets larger, then the number of those cycles that pass a given point in a second goes down or decreases, okay? So think about this for a moment, about frequency, because it is super important. We're going to be using wavelength and frequency quite often. Now, the unit, or I should say the symbol for frequency, is either this funny looking B called mu, or an F for frequency, okay? And so we'll be using these two symbols interchangeably, okay? Now, what are the units of frequency? Well, they're either going to be what we call cycles per second. So in other words, it's the number of those cycles that we just talked about that pass a given point in 1 second, or hertz. So kind of look at it in this terms. Let's say you have 1 cycle per second. That's equal to 1 hertz, okay? 1 hertz. Or let's say you have 2 cycles per second. That's equal to 2 hertz, okay? Hopefully you kind of get the idea there. Now, often we'll also write cycles per second in the simply reciprocal manner, where, for instance, in this case, the 2 cycles per second could be written as 2 seconds minus 1. And this basically means cycles per second. So this is the same thing as this, okay? It's just in the reciprocal form. And so we'll often write our unit for frequency as in this manner here, okay? All right, and then we've talked about amplitude already. All right, so let's move on here. So I've already talked about that a standing wave is considered a big aspect of the nature of light. Light tends to have a nature of standing waves. Um, so what we're going to turn to is this term electromagnetic waves, okay? This is a really fancy term for light, okay? It's a more of a scientific term, but a electromagnetic wave is referred to as a standing wave. In other words, it's light, okay? So to continue our discussion with light, we need to understand that during the essentially 18th and 19th century, scientists were very interested in electricity and magnetism. And they knew that electricity was a force and magnetism was a force. And we knew that, remember, we've already talked about electricity a little bit, that electricity creates an electrical force known as the electrostatic force, right? And electrostatic forces are important because they create the attraction between opposite charged particles, positive and negative. And so electricity is associated with that electrical force or the electrostatic force of positive and negative charges. Magnetism is also characteristic of matter, and it is a force that radiates out of particles, but it's not a force of charge. It's a force of positive and negative magnetic poles. And we're not going to talk a lot about that in this course. You can get more about magnetism in physics. But what I want you to understand is that during the 19th and 18th century, as scientists began to study these two forces, they began to make a clear connection that magnetism and electricity, these two forces might not actually be separated, but they're actually united or connected in some way. Michael Faraday, who you don't really need to know for the test, but I want to bring Michael Faraday into this so you can kind of get a historical perspective of some things. So Michael Faraday is going to be one of the first scientists to really make this connection of looking at electricity and magnetism of being connected. In other words, we're really saying for the very first time that two forces in nature are actually connected to one another. Michael Faraday is going to make this claim, but Michael Faraday is going to make an even bigger claim, and he's going to say that really this connectivity of electricity and magnetism is really light. So in other words, a combination of both of these forces generates what we now know as light, okay? But he couldn't really prove it. But he had a good friend, James Clerk Maxwell, who was a brilliant mathematician who actually did prove that electricity and magnetism were indeed connected to one another, proving a Michael Faraday statement, okay? But he did so mathematically. James Clerk Maxwell did, unlike Michael Faraday did. What James Clerk Maxwell realized is that electricity and magnetism both produce standing waves. And these two standing waves are indeed connected with one another. And he referred to them as electromagnetic waves. And when he determined the speed at which an electromagnetic wave traveled, he determined that it was 3.00 times 10 to the 8th meters per second. Okay, super fast. Well, it was known at this point what the speed of light was. In other words, how fast light traveled through space. And it was known that light traveled through space at 3.00 times 10 to the 8th meters per second. So James Clerk Maxwell made the connection that electricity and magnetism, those standing waves traveling at that speed, the same speed that light does, makes the connection that really light and electromagnetic waves are really the same thing. And so, therefore, Michael Faraday and James Clerk Maxwell over time gave the evidence that electromagnetic waves, or in other words, electrical and magnetic forces, are not only connected, but they are light waves. Okay? Now, let's dive into what we refer to as these electromagnetic waves, their characteristics a little bit more. So I have a diagram, this is in your notes, of an electromagnetic wave. So essentially what you can think of is that the two waves, so electricity or the electrical field is going to start producing a standing wave that's going to propagate up and down like this, okay? So this is our, oops, that is awful. See, I can't draw us very well here. But hopefully you get the idea that essentially our electrical wave is moving up and down like this. And then that's going to create the magnetic field. And the magnetic field is going to be perpendicular to the electrical field. In other words, the two waves, okay? So let's say I'm going to create the electrical field, standing wave. It's going to go up and down like so. But the electrical wave is going to be perpendicular. So essentially, they're going to be traveling like this, perpendicular to one another. But the two waves are connected to one another, all right? And really, again, maybe it's hard to comprehend, but those two waves are creating the electrical force, or that electrostatic force that we've talked about, and the magnetic force that we've associated with, okay? Now, the two waves are going to have wavelength, just like any standing wave, and the wavelengths for both waves are the same. The amplitude for both waves are the same, and the frequency for both waves are the same. So everything is the same there. They're even moving in the same direction. They're propagating out from our oscillating source in the same direction. And they're just, the only difference is that they're traveling perpendicular to one another. And one is creating an electrical force, and the other one is creating a magnetic force, okay? All right, so in your notes, here's some important points to write down about these electromagnetic waves. So first of all, when we refer to a wave, moving up and down, back and forth, whatever, we're talking about that it has oscillations, okay? So what we're gonna do is focus on oscillating electrons, okay? Now, electrons, they are going to oscillate in atoms, and even free electrons that are not in atoms are going to oscillate, okay? Now, obviously, these oscillations are going to start producing energy, and the energy that these oscillating electrons are going to produce is electromagnetic waves, in other words, light. So we can say that electrons, because they are charged particles, okay? So we're just using an electron as an example, but any charged particle behaves in this manner. As an electron is oscillating, it's going to start emitting energy in the form of electromagnetic waves, or in other words, light, okay? By the way, we use the term EM as a short way to express electromagnetic waves, so EM. All right. Let me actually underline this. So EM, electromagnetic waves. Now, electromagnetic waves are also called electromagnetic radiation because the waves radiate in all directions from an electrically charged electron or any electrically charged particle. Okay, so any charged particle, this electromagnetic radiation or light radiates out. Okay, all matter has charged electrons, right? So therefore, all matter is going to emit light. Everything emits light that is made up of electrons or charged particles. So since you are made up of electrons, there are electrons all over inside you, those electrons are going to oscillate and emit light. So you are a light emitter, okay? You emit light. Your desk emits light. Your food emits light. Everything emits light, okay? Because it's made up of electrons. And that's important to make sure you understand. All right, so an oscillating electron then is going to create a charging electrical field, which produces a charging magnetic field perpendicular to it. And that's where we get the two waves, right? The electrical field and the magnetic field that are perpendicular. And those waves are those electromagnetic waves that are radiating out. So the two waves will travel together as one electromagnetic wave. Now, the electromagnetic waves, they do travel through empty space, as well as air and other materials. Now, this is kind of unique to electromagnetic waves because most waves don't travel through empty space. They need some kind of material to travel through, like water waves need water to travel through. Seismic waves need the earth to travel through. Sound waves needs air to travel through. But light waves, they don't require material matter to travel through. They can travel through empty space, and that's important to remember. All right, light can travel through all sorts of objects and through empty space, which is awesome. All right, all electromagnetic waves travel at the same speed. Okay, all electromagnetic waves travel at the same speed. Now we'll look at that a little bit more in detail in a bit. But the speed at which they travel, at least in space or empty space, a vacuum, is 3.00 times 10 to the 8th meters per second. So when light travels through different materials, it will travel at different speeds. But for our class, we are going to be concerned with only one speed of light, and that is the speed at which it travels through empty space or a vacuum. So I really need you to know this value, the speed of light of 3.00 times 10 to the 8th meters per second. The speed of light is symbolized by the letter C. So when you see C, we're talking about the speed of light, 3.00 times 10 to the 8th meters per second, okay? And so that's the units of light speed, all right? And of course, light waves, we've already referred this, light waves are electromagnetic waves, okay? Electromagnetic waves is more the correct term for light in the sense of it has more explanation than when we simply say light, okay? More vastness to it, I guess. Okay, so again, we look at our diagram of our electromagnetic wave. Two waves, the electrical wave, the magnetic wave, and both of them are perpendicular, traveling in the same direction, same wavelength, same frequency, same amplitude, okay? Here's another look at it. This is not in your notes, but you can kind of see the idea. You have the sense you get the electrical field going up and down like this in the red, and then in the blue is going to be your magnetic wave. And again, they're just traveling perpendicular to one another. But the same wavelength, there's the wavelength, right, from crest to crest, that's the wavelength. You got the wavelength here from this point to this point, and this wavelength is the same as this wavelength. They have the same frequency, same amplitude, okay? However, remember, they do result in different types of forces though. One is an electrical force or an electrostatic force, and the other one is magnetic force. And it's really the electrostatic force that we most need to really understand. And so you can essentially say then that light holds particles together then, right? In a lot of ways. All right, now let's get into our last bit of this lesson, and that is really the importance of what we're going to call the electromagnetic spectrum, okay? Now, I think most of you know that if you take white light and you pass it through an object like a prism, the light bends and it creates a rainbow of colors, okay? And you can see this with a variety of other objects. In fact, after it rains in the sky, a lot of times you will see an actual rainbow. And it's the rainbow that you see in the sky is having the same effect as you see white light going through a prism. You're just bending the light and it's creating a separation of light into a rainbow of colors, all right? You can do this with DVDs and many other objects, okay? But what we're gonna do is we're gonna focus on what these colors really mean, what they represent here. So as you bend light through the prism, as is depicted in this diagram here, the different colors represent a result of different electromagnetic waves, essentially, okay? So the difference between these different electromagnetic waves are the wavelengths, and you can kind of see that here. These red ones have wavelengths that are much larger. Let's see if I can actually draw this a little bit. So the red ones have a wavelength from here to there. So notice that the wavelength is much larger here than it is on violet light down here. Okay, the wavelength on violet light is much smaller. So what we're saying is that white light is actually a mixture of different electromagnetic waves. Now, all of those waves are still light waves, okay? It's just that there are different light waves, essentially, or different electromagnetic waves, and they differ by their wavelengths. As a result, they're also going to differ by their frequencies. Now, the reason why we see them as different colors is because your brain, when it picks up that particular wavelength and frequency, the brain has the ability to transfer that information into a color. So red looks red because the electromagnetic wave that's creating red light to us has a certain wavelength and a certain frequency that our brain determines that information as red or orange or yellow or so forth like that. So all I'm saying is that there are different electromagnetic waves out there, and those differences are based on their frequency and wavelength, all right? And so again, white light is a mixture of all the colors that we see in the rainbow. And it's important to note those colors. I need you to know the rainbow colors. And a lot of people use the term Roy, red, orange, yellow, Roy G. Biv. All right, Roy G. Biv. Now that's an acronym to use red, orange, yellow, green, blue, indigo, and violet. So it kind of gives you the colors of the rainbow in order that you need to know, and those colors, okay? So honestly, those, as you're gonna find out in just a minute, the wavelengths are getting larger as you're moving from violet to red. So in other words, red light has the largest wavelengths and violet light has the smallest wavelengths, okay? Okay, so you can see the rainbow of colors with the CD here or the DVD. You can see those colors, you can see the reds, which have the largest wavelengths, and the smaller wavelengths are the violets, okay? All right, now this diagram that's right here in your notes is super, super important, okay? Become very familiar with. This is known as the entire electromagnetic spectrum. This is all of the electromagnetic radiation that's out there in space in the universe, okay? And we go from radio waves on one end of the scale, so AM radio waves, all the way to gamma rays on the other side, okay? And in the middle is the visible spectrum. Now, the visible spectrum is the rainbow of colors that we're familiar with, the red, the orange, the yellow, the green, blue, indigo, and violet, Roy G. Biv, okay? So what I need you to know is that all of these forms of electromagnetic radiation are forms of light or different forms of light. However, we cannot see any of these forms of light except for what's in the visible spectrum, okay? So this visible spectrum is what gives color to our world, and is basically because the wavelengths of these forms of electromagnetic radiation is enough information that our brain can interpret it as a particular color. So we cannot see radio waves, we can't see microwaves or infrared or ultraviolet, X-rays or gamma, but we can see the visible spectrum waves, okay? I hope you understand that. Now, I need you to know some things. I need you to know that on one end of the spectrum is radio waves, and on the other end of the spectrum is gamma. And then on this side of the visible spectrum is ultraviolet, or in other words, UV light. Ultraviolet, thinking that it's nearest to the violet color, right? So right here is going to be the UV light, UV, okay, next to violet. And on the other side, right, of the spectrum is going to be what? Infrared, what we call IR, okay? IR is infrared light next to the red, okay? Ultraviolet next to violet, infrared next to red, okay? So I need you to understand a little bit about where these electromagnetic waves fall into the overall spectrum, okay? Now, as far as wavelength and frequency, okay, this is super, super important about what I'm about to share with you. Okay. So, as you are moving across the spectrum, all the way from the gamma towards the towards the radio, okay? As you're moving in this direction here, that's awful arrow. Geez, I cannot draw a straight line with this worth anything, okay? But essentially, as we're moving in this direction from gamma to radio, the wavelength is increasing, which is indicated right here, okay? The wavelength increases going from gamma to radio, okay? Which means that in our visible spectrum, the violet light has a smaller wavelength than red light. The red light, the largest wavelength. So in reality, you could say that wavelength is increasing in this direction in the visible spectrum. Frequency is going to go in the opposite direction. The frequency actually increases in the reverse direction, okay? So we kind of get what we call an inverse proportional relationship between frequency and wavelength. In other words, what we're going to say is that gamma has the smallest wavelength, but the highest frequency. And over on the other end, we're going to say that radio waves have the largest wavelength, but the smallest frequency. So in the visible spectrum, red light, large wavelengths, smaller frequency; violet light, small wavelengths, but high frequency, okay? And so hopefully you kind of get that perspective there. All right, so here's a few things to jot down in your notes. Again, the different types of electromagnetic radiation exist. They differ only by their wavelengths and frequencies, okay? Only by their wavelengths and frequencies. Now, the entire range of the electromagnetic spectrum or waves makes up what we call the continuous electromagnetic spectrum. And why do we call it continuous? Because the spectrum continues to basically merge into the next wave without any breaks whatsoever. You can kind of think of the rainbow of colors, they just kind of merge in with one another. And so you get a gamut or a rainbow of colors that are all continuous. All right, there's no gaps. It goes from red and then merges into the orange, moves into the yellows and the greens and the blue and the golden violet, okay? And it just merged into one color into the next without any breaks. And so that's why we call it a continuous spectrum. All right, so again, you can see with this prism, you get a rainbow of colors, continuous spectrum in the visible from merging colors from reds into oranges, yellows, greens, blue, indigos, and violets, okay? And so you can see that if you have colored pencils, you can color this in, but what I want you to see, this is what we call the continuous visible spectrum, the rainbow of colors that merge into one another. The reds merge into the orange merges into the yellows, and then the yellows merge in the green, and so forth and so forth, okay? So if you want to even color in these particular spectrum, to remember that this is the visible spectrum of our rainbow, and it is continuous, okay? Continuous. I'm gonna keep on clarifying that. It's really important. All right, so finally, again, what is the absolute relationship between wavelength and frequency? Well, it's an inversely proportional relationship, okay? And what we're saying is the wavelength, okay? The wavelength, if it goes up, the frequency, remember this is lambda, the frequency is gonna go down, okay? So we're gonna use mu, okay? This weird V looks. So as the frequency goes, or sorry, the wavelength goes up, the frequency must go down. They must be in inverse relationship to one another. Mathematically, we can state that in an equation, all right? And that is the speed of light. Now remember, the speed of light has to be constant. It cannot change. All electromagnetic waves travel at the same speed, the speed of light. Remember that the speed of light is 3.0 times 10 to the 8th meters per second, okay? So the speed of light, symbolized by c, is equal to the wavelength times the frequency, okay? And in this equation right here, gives us the inversely proportional relationship. As the wavelength goes up, in order to keep light at a constant speed, if that goes up, then this must go down to keep that constant, okay? So keep that in mind, inversely related. Now this equation, I will need you to know have it memorized. We're going to be working with it. I'm going to have you solve problems. So I'm going to give you the speed of light and the wavelength, and you solve for the frequency. I can give you the frequency and the speed of light, and you solve for the wavelength. Okay, so those are important concepts. Now, the last thing I want to do with this is to look at the units. Remember that the speed of light has units of meters per second, okay? So the units have to be in meters and seconds. Or if I take the reciprocal, it would be meters seconds to the minus 1, okay? Those are the units for speed of light, right? Now for wavelength, because we're using distance in meters, the wavelength must also be in meters. And frequency must be in cycles per second, okay? Or per seconds, okay? In other words, 1 per second, okay? In order to use this equation of the speed of light is lambda, let me redo that here, erase that. And mu, like so, okay? So make sure that you have this all written down, these units, and don't forget that. I have a lot of students that will make mistakes in their calculations because they're using the wrong units in the calculation. They'll use nanometers instead of meters, but they have to be in meters in order to use the wavelength here, because the speed of light is in meters, okay? All right, so there you got it. There's the wave nature of light. This is what you really need to know about the wave nature of light, is what's in this lesson. So I would go back and really study your notes really well, put this all together, because I've given you a lot of information here, okay? So that's it for now, for today, okay? So we'll see you next time.